Welcome back, everybody. This is episode 20. Welcome back, everybody. This is episode 20, and it's covering off the cockpit section for Hawker Typhoon JP843. Recently, I've had a couple of really great questions about the progress on Hawker Typhoon JP843's cockpit section. I really haven't done a lot of dedicated video on this one, and it's a major aspect of the project, so I wanted to cover it in great detail for both paid subscribers and our YouTube subscribers so you can really see what's going on with our progress, understand how these structures were built, and understand some of the compatibility between the Tornado, Typhoon, and the Tempest aircraft. Now, the Typhoon, the Tornado, and the Hawker Tempest, they really bridged the gap between the tubular structure that was used in earlier designs and monocoque, semi-monocoque structure that was used in later designs. And the Typhoon is really the first production aircraft that saw this bridged structure design, and that was done by incorporating the tubular structure for the entire cockpit section and an integrating structure that combines the tubular structure to what was a semi-monocoque structure for the fuselage after the cockpit. The Hawker Typhoon's cockpit structure is part number E101500, and this is the assembly part number for the overall tubular section that contains the engine and all the main systems, as well as the pilot seat and the cockpit instrumentation. When we look at the overall structure of this cockpit assembly, there's a few really key joints. And the joints are going to be for the Spar carry-throughs, so what they call panel BC and panel HK. BC being a panel made up of 4 different points, which are all of the forward spar, wing spar attachment points, and they carry directly through the cockpit from wing to wing. The same goes for panel HK. This is the rear spar attachment points, 4 points again, and it attaches the rear spar straight through the cockpit section. These are very heavy forged fork ends that the wing pins go through and carry the loads into the structure. An important thing to note about panel BC is that B, the top strut, or the top spar carry-through, is actually also the rear foot mount for the Napier Sabre engine. And this is one thing that actually led to a lot of vibration being transmitted directly from the propeller and engine into the structure of the cockpit, and some of the vibration problems that were seen in early Hawker Typhoon operations, and for that matter throughout operations. There is other ways of developing this, including rubberized mounts that were put on there, and they all helped reduce it. New balancing of crankshafts in the Sabre, it was all big, but ultimately the vibration continued to be transmitted directly from the engine into the spar and right into primary structure. As a side note, that was kind of fixed with the Tempest because they had to extend the Tempest cockpit structure and add a fuel tank, and when they did that, the Sabre actually mounted to a forward member, not the main spar, so it reduced vibration quite a bit from there. Another main joint is joint A, and joint A is the forward Sabre engine foot mount, and it has a couple struts that go directly down, and it connects to panel BC as well, so that front section is very heavy. And a couple other big critical ones are joints L and M, L being the topmost rear corner of the cockpit, and M being the lowermost rear corner of the cockpit. And these are the joints that have forged fittings that attach to the integrating structure and ultimately into the aluminum structure, or the monocoque section, starting at frame A. So these and all areas of the cockpit structure are essentially made up from cockpit joints and strut assemblies. So we'll dig into these, and I'll attempt to break it down on how these areas are built up as subassemblies. So a typical strut assembly is made up of a tube and a plug end. In some cases, there's one plug end at one end and a squared section at the other. In some cases, there's a plug end at both ends. In some cases, there's no plug ends and only squared ends. So it really varies throughout the structure. But essentially, a strut is made up of, at the very least, a tube with some sort of mechanical fasteners that attach it to the joints. So the basic assembly of a plug end to a tube is that the plug end has a reduced diameter and fits directly into the tube and is then either bolted or riveted with tubular rivets. Now there's a couple exceptions to this. One that I can think of off the top of my head where the tube is actually not left round but squared and then has a plug end put on it. So aside from using plug ends, squaring these tubes was Hawker's other mechanical means of attaching these struts to the cockpit joints. So Hawker's tube squaring process was a cold working process that was done by a hand-operated machine in a set of dies, and it would actually roll the round tubes into a very accurate predetermined square or rectangular size that would allow fitting of flat plates to the tube. And then these joints could be assembled with various other hardware. Ultimately, these struts, regardless of what other kind of end they have, whether it's squared or a plug end, and believe me, there's a lot of different kinds of plug ends, they could be assembled into one little sub-assembly and then attached to all of the cockpit joints to help create the larger assembly. It's important to understand the hardware that makes up both the joints and the strut assemblies. And a lot of different manufacturers use different standards. Some exceptions to this are things like AGS, which is Aircraft General Stores, and there is some of that used throughout the Typhoon, but a lot of it is actually manufacturer-specific hardware. And especially when we get into the primary structural areas of these strut and joint assemblies, when you start looking at the bolts that are in there, they are Hawker part numbers or Hawker standard part numbers. With bolts and our next component, tubular rivets, the assembly would be essentially the same. And if we use an example of a strut that has a plug end being fitted to it, the plug end would slide into the end of the tube, the holes would be drilled through the tube, usually perpendicular to each other, and then the ferrules are installed into those holes, bolt is placed in, associated hardware is put on, and it's tightened down. The same would apply to a tubular rivet, where the hole is drilled through that assembly, the ferrules are pressed into place, and then the tubular rivets pressed in and basically flared out at either ends to keep it in place. The tubular rivets are no exception to Hawker special part numbers. They're either specific part numbers themselves or another A standard, primarily A standards of many different lengths, diameters, and wall thicknesses, but they are also prevalent in these assemblies and add, again, to our list of parts. Ferrules are essentially a small hat section bushing that gets pressed into the tube or the plug end, whatever the bolt or the tubular rivet's going to go through, and it acts as a bushing to prevent damage to the surrounding structure during the installation and operation, essentially, of that assembled joint. Now, if there's a problem with the bolt and bolts are coming and going and rivets are being drilled out, the ferrule acts as a sacrificial piece that can also be replaced instead of having to replace damage or wear on the strut or the plug end itself. In addition to the ferrules and the bolts and the tubular rivets, some of the lighter structural assemblies also have distance tubes. And a good example of an application for this would be that you have a squared tube end of a strut, and that fits in between two stainless steel gusset plates at a joint. A bolt goes through all of that assembly, and when you tighten the bolt, there's compression on it, and it wants to squeeze that assembly together and could lead to some deformation of components. So what's done is the assembly is put together, and in a lot of cases, Hawker would wire a distance tube in place while the bolt's assembled, so it takes up the gap in between any open air of that joint assembly and allows resistance for compression and prevents deformation of any of the components therein. There's only really a couple types of joint assemblies in their basic form that are used in the cockpit for the Hawker Typhoon. And I think a lot of you are probably familiar with the stainless steel gusset plates that Hawker used for a lot of these mechanical joints, and it's prevalent in the Typhoon as well. They're quite a heavy gauge stainless steel joint, and there's often flanges formed on them. Compound curves are just straight edges to help make the assembly more rigid. But they're plates that are placed on either side of an assembly of different struts with bolts that go through them to hold everything in place. All of these are put in, and almost every one of those fasteners is reamed when they go through there, and the tolerances that we've found are absolutely beautiful in it. Now, there's other joint assemblies for a lot of that very, very heavy structure, a good example being the wing spar fittings. There's flanges that are forged directly into the large fork ends to which the struts can attach, and any plug ends can be attached through bolts. Again, almost everything that we've seen is a very high tolerance press fit in these locations. But that really describes the two primary joint types that we see when we're working on the cockpit section. In some lighter structure and supportive struts that you see throughout the structure, one end of the strut itself may be attached by a lug, so an individual lug that's bolted through other hardware that's already there or specific hardware to retain the lug itself. Once all of these sub-assemblies are built into one large assembly, being the cockpit structure, there's still a lot of other brackets and fixtures that go on it. I won't go too far into them because there's so many of them. A lot of them relate to systems, and they're just little clamps that are attached around the tubes of the tubular structure to hold each individual system component from vibrating or fretting or any of that stuff. But another one that we've got quite a bit of design work done on is just the standoffs, or for the ML fasteners on all the cowling panels. There's standoffs that are attached to this tubular structure that allow for the receptacle of the fastener to be held in position. And these are all over the place along this structure, all different angles and different shapes and different lengths to make sure that it holds the cowlings in the correct position. As you can imagine, with the kind of complexity that we're dealing with here, it was quite apparent right when we started the project that the cockpit section was going to be a massive undertaking, and really it has been since the arrival of the cockpit section that we purchased from Roger Marley. Every effort has been made to start developing data and identifying questions that need to be answered so that we're going to be able to put this assembly to work. Now, essentially that's 2015, and there's literally been thousands and thousands of man-hours put into this for developing data and confirming data, identifying missing components, working with people around the world to share information, loan components, and really make the whole structure assembly come together. So one of the first things that we require after the design and verification process is complete is to have a place to build this. And the fixture for the cockpit section has to be incredibly accurate, and it has to be very rigid because of the accuracies required for the assembly. You may have seen in past episodes, I've done one on the fixtures that we've produced here. We have a fixture table. It's approximately 6,000 pounds. It's a monstrosity, but it's going to keep our tolerances where we need them. And once we build it up around the assemblies that we have and dial it in using the skills of E3D technology again, we'll have the perfect platform to assemble JP843's cockpit. In addition to the fixture, there's also some special equipment required for the Hawker tube squaring process, and that's a Hawker tube squaring machine. The original Hawker tube squaring machine was hand operated. It was the two rollers driven by some fairly aggressive gears, but it suffered from an issue where on the larger diameter tubes, the gears didn't mesh and only one roller would drive. And I wanted to address that in the construction of our machine. So our machine is actually a chain-driven machine, and it's got a tensioner in it. So throughout the range of die diameters and tube diameters being fed in, we'll always have positive engagement of both rollers. In addition to that, I was concerned about mechanical advantage. Knowing that this would be a very laborious project, I've acquired a 10-to-1 gear reducer, and I'm going to locate that under the bench that I've also made for this assembly to, again, reduce the amount of effort that has to go into these tubes and increase the accuracy, or I guess control and slow the feed of the tube itself into the die. So the idea here is that we'll end up with a very controllable, very accurate, and somewhat easy to use machine to make sure that we're respecting Sydney Cam's design efforts. All of this work on the tube squaring machine is nothing without dies. They're really the heart of the beast, and thankfully Bruce took that on a couple months ago now, and we were able to design and build up a die set of almost every one of the Hawker standards, specifically every one of them for the Hawker Typhoon and a couple other types as well. So those designs are done, everything looks good for them, and our friend Brian is going to produce the first set of dies and a series of shims that are involved with the process for us to evaluate and test on some tubing as this machine goes together. Design, fixture table, tooling coming into place. Well, the other requirement is going to be material. We've got almost all of our struts actually rough cut already and ready for the next step of the process. At the moment, they're put to the side, they're oiled to prevent any kind of corrosion, but they are ready and we're in good position there. Another area is basically the basis of the foundation of building the cockpit section, and that's the wing spar fittings. So massive amount of material expense required in that, and we've got it. We got it again quite some time ago along with the tube, and we've got it sitting here in the shop ready for machining once we've kind of dotted our I's and crossed our T's with the regulatory requirements of production there. Another key aspect of the build is, of course, the hardware. There's a huge amount of engineering and development work that's gone into this, but we're really ending the near of it, and it's so exciting that we're going to be able to produce these exactly as Hawker did to make sure that JP843 is bang on. One more thing I should touch on for this episode is actually compatibility. The Hawker Tornado fitted with the Rolls-Royce Vulture engine actually had the datum line for the aircraft, or the thrust line of the aircraft, positioned slightly differently than that of the Typhoon. It was 1.7 inches lower than the Typhoon's thrust line. And not only that, the wing itself was fitted a little over 4 inches lower, again, than the thrust line, and 1.7 inches lower than the Typhoon. So you can see that you're getting closer to 6 inches differential between the location of the wing on the Tornado and the Typhoon. And when you think of all those little struts in there that are all connected to these points, all those struts have to change. Some of the angles and the geometry of the cockpit have to change. So it leads to a lot of substantial difference. The Tempest, as many of you may know, was actually designed as the Typhoon 2, and it was an attempt to address the thick wing on the Typhoon. So they put a much thinner wing on it. It relocated basically panel BC and HK. It compressed those into much shorter variants, and again, it changed the length and the design of a lot of these smaller strut assemblies. And then you add to that the fact that the Tempest took the fuel capacity from the wing and put it forward of the firewall. It extended out the engine mounting forward of the main spar, which was a blessing in disguise because the vibration was no longer transferred directly into the main spar. But it pushed it forward, so there's more joints and more structure required on the Tempest there. Now, that's not to say there's not compatibility. Nicholas was really good at this, and it takes us quite a bit of research because the Typhoon, the Tornado, and the Tempest, well, some of the struts and some of the geometry on plugins might be different. Some of it's the same. So if you have a strut assembly number, it could be completely different. Like with the Tempest, almost all of them are different, but it could contain sub-assemblies or sub-components that are used throughout all three designs. So they look very similar. There is some crossover, but you really have to work to find it. And when you do, it can really help with the Typhoon build. One point of note is that joints L and M, these are the joints that attach the integrating structure to the cockpit and the monocoque structure to the integrating structure. This whole assembly area is very, very much the same. So there's some nice crossover in there that has helped us. If you haven't already subscribed to our YouTube channel, guys, please do. Every subscriber helps. And also, if you're able to, please consider heading over to our paid subscription channel, where for just a few dollars a month, you'll get all of this content ad-free, as well as access to our forums, direct communication with myself and other team members, as well as a host of other benefits that we're working on now. This program has really helped us out, and every one of the contributors to that channel have made a massive impact on our progress over the last little while. So please consider that if you can. But until next time, guys, take care, stay safe, and we'll see you soon.